Okay, Chapter 10, Experiments. So we've talked a lot about how there are, about the inability to 100% conclude causation from correlational research, and we're going to talk about how with experiments you can conclude causation. Okay, so here's an example of an experiment referenced in the textbook. There were two groups of students. They were assigned to either a laptop group or a notebook group, and they took notes on one or the other while they watched a TED Talk, and afterwards they were scored on they were given a test to measure their knowledge, how well they remembered the talks, and the paper and pen group scored significantly higher on conceptual knowledge. The other study was done in babies, where they observed an adult either persist in doing a difficult task or not persist, not expend effort, and then afterwards they were given a little toy that looked like it was supposed to play music, and there was a button on it that looked like it was supposed to trigger it to play music, but instead it did nothing, and they wanted to see how many times the babies would try to push the button, how long they would persist, and the ones that observed the effortful condition persisted longer. Okay. So it's not an experiment unless there's some kind of manipulation, okay? Unless there's an active manipulation of the environment, a manipulated variable, and then a variable measured in response. Okay, so the manipulated variable in an experimental setting is the independent variable, or IV. It's going to have different levels that denote the different experimental conditions. So if you have an experiment in which participants are assigned either a drug or a placebo, and there's just those two groups, then it's got two levels. Or you could have 3 or 4 groups, laptops, notebooks, tablets, nothing, for example, in that note-taking study. Okay, the dependent variable is the measured one. It's kind of easy to get these two confused. Just remember that the dependent variable in theory depends on the independent variable. Okay, if there really is a relationship between the two you observe. Okay, you could also remember that DV, the dependent variable, is the data. That's what you're actually measuring and recording. And they both start with D. Okay. Control variables are technically not variables. They don't vary. They should be held constant between the different levels of the IV. Okay, so this is just all the other factors that should be identical between the different levels of the IV, and so it's only the IV that's changed. Okay. So with experiments, you can meet all 3 criteria for causal claims: covariance, temporal precedence, and internal validity. And so covariance, basically that means that if the IV changes and the DV changes as a result, the DV will vary with the IV. Okay. Temporal precedence, this is time. Okay, so first you manipulate the independent variable, and then afterwards you measure its effect on the dependent variable. Because you have a cause variable, and then you have the effect variable that follows. Okay. Internal validity, basically, if an experiment has internal validity, which it can, then the IV and nothing else is responsible for changes in the DV. Okay, the blame is squarely on the IV, which is what you want. Okay. All other factors have been controlled for. There are times, there are instances in which things can go wrong, in which experiments were not designed properly, and that's when you have confounds. Okay, some other potential alternative explanation for changes in the DV. Sorry, text got cut off there a little bit, but design confounds, that's where you have accidentally, unaccounted for additional variables. For example, in the laptop study, maybe you had differences in question difficulty on the test that were given to the students, in addition to the difference in note-taking method. Okay, so if you saw differences in test scores, you wouldn't be able to know if that's due to differences in note-taking strategy or just question difficulty. Okay, so you need to have them fill out the same questions in both, okay, or at least ones that are matched for difficulty. Okay. You may have variability between participants in the different groups, experimental groups. Okay, that may or may not be a problem. It's really only a problem if it's systematic. Okay, so if it really varies systematically with the IV, if it's an issue with the experimental system. Okay, if it's unsystematic variability where it's just random, then it's not an issue. Okay, so this is kind of an illustration. Say in the effortful condition, there were babies. You have this variety of babies, some that just had a nap, some that need a nap. Okay, and of course they're going to vary in their responses to watching the effort and in their persistence. But as long as you've got variability that also exists in the other one, and there's no real tie between this variability and those two levels, if it's just random and haphazard between the two, then it's not an issue. The way that you can ensure that that's the case is using, or one thing that you'll do is use random assignment. Okay, so you of course don't want to, as the experimenter, assign all the happy babies to one condition, all the sad babies to the other one. So that would be an example of a selection effect. Also, if participants are able to self-assign, then you're going to have selection effects there too. Okay. So this data here, I don't know if this is real or not, but the example study was investigating a new intensive treatment for autism. There were some parents who insisted on being in part of the intensive treatment group because it was very inconvenient for them to come to the study site, etc. So in the end, you had non-random, it wasn't completely random selection between the two, and you couldn't determine exactly what the cause of the difference between the groups was. Okay. One way that you can ensure that the individual differences between individual differences in the subjects are balanced between your two groups is to use matching. Okay, so you might have, so maybe for example in the note-taking study, I say I don't want there to be just by chance a bunch of higher GPA students in the note-taking group versus the laptop group. And so you would distribute the groups or assign the groups after doing some matching. So you'd rank them from highest to lowest GPA, and then you'd then have pairs in order, the two highest participants on down to the two lowest, and then within each of those pairs they're going to be randomly assigned, where one goes randomly to one group and one is randomly assigned to the other through like a coin flip. Okay, so then at the end you're going to have an even distribution of GPAs between the two. The GPA levels should be basically the same between the two. All right, there's another part to this, but that's the end of this